In this talk, we'll be looking at RPC middleware for enterprise systems. Essentially, we'll be focusing on the fundamentals of distributed systems, how distributed systems work, what are the main principles, what are the main things that we need to look at when developing middleware to enable distributed systems to work. We will be covering the following topics. We'll start with an overview and design issues for middleware for distributed systems. We'll look at some of the protocol issues, what kind of rules can we embed within middleware to enable them to work reliably. We'll look at the RPC execution model, parameter passing, how parameters are passed when comparing between parameter passing in local systems versus parameter passing across networks. We'll look at binding, how do you locate a server and eventually locate the service that you want to use, and how do we treat failures, how a failure is treated in different models of middleware. Here we delve into the typical interaction pattern in RPC middleware. So we'd like to highlight essentially the fundamental client-server communication workflow, which is probably the most common communication pattern within distributed systems. So in a typical interaction, what happens is that the client, usually a user process, sends a request message to a server, and once the message is sent, the client enters what we call a blocked state, which means it pauses its operations and waits for a response from the server. Upon receiving the request, the server performs the required task or work as specified in the client's request. Once the server completes the task, it sends back a reply or result to the client. So once the client receives the server's reply, it unblocks, meaning it can resume its operations now that the requested data or the result has been received. So within the diagram that we see, the simple diagram, on the left we see the client initiating the process by sending the request. The action is represented with an arrow pointing towards the server. On the server side, the request is received and processed, and the result is sent back. Finally, the response travels back to the client, allowing it to continue by unblocking after receiving the wait reply response from the server. So what we're trying to emphasize is the synchronous nature of RPC middleware interactions, where a client must wait for the server's response before proceeding with doing anything else. The approach is common in systems where immediate feedback from a server is required for the client to do their next steps. However, it also highlights a potential limitations. Clients can experience delays if server processing takes time, and this affects overall responsiveness. So here is another visual representation of the client-server interaction. In an RPC, remote procedure call model, highlighting the sequence and timing of request and response. So at the client side, the interaction begins with the client initiating a request to the server. Once the request is sent, the client enters a wait for result phase, also the same as the blocks phase that we mentioned earlier. So during this time, the client is essentially blocked, meaning it cannot proceed with further operations until it receives a response from the server. At the server side, after receiving the client's request, the server begins to provide service. This represents the period during which the server processes the request, performing any necessary computations or data retrieval to prepare the response. Once the process is completed, the server sends a reply back to the client. And on completion, the client receives the server's reply and it is unblocked, allowing it to proceed with its next operations now that the requested data or outcome is available. So key takeaways from this diagram is that the interaction showcases the synchronous nature of RPC calls, where the client remains idle, waiting for the server to respond before it can continue. Now this, as we said earlier, this approach is simple and effective when quick responses are required or expected, but the problem is that it can lead to latency issues if the server takes a significant amount of time to process the request. This blocking mechanism is a fundamental design aspect of RPC systems, impacting the overall responsiveness of client applications in distributed systems. When transmitting data, it's important to consider the network over which it will travel. So different networks have unique requirements, and each imposes limitations on aspects like the maximum message size, often restricting packets to a few thousand bytes. So to ensure a successful transmission, the middleware in conjunction with the network stack must transport messages in a format compatible with the network itself. It's not as simple as sending data directly. Instead, messages need to be encoded in a language that the network understands. One essential process is message fragmentation and reassembly. This involves breaking down the data into manageable packets, translating it to match the requirements of the internet, and then reassembling it upon arrival to maintain coherence. As messages cross multiple networks with varied technologies, for example, ATM networks where packet sizes may be as small as 56 bytes, or Ethernet networks that have a limit of around 1,500 bytes. So the middleware must be adaptable. It needs to be aware of these network differences to fragment and reassemble messages. While lower layers of the network stack usually handle fragmentation and reassembly, middleware may also need this awareness to adapt to diverse network technologies. We can generally assume that a fragmentation and reassembly protocol is already in place, provided by the network stack. However, the middleware still needs to define the message types required for the procedures involved. It must establish the communication protocol and identify the message types needed to support it. So next we'll explore the basic message types that underpin any protocol. This slide addresses different message types in RPC, each serving a distinct role in client-server communication, with some of these message codes being so important that they are embedded in the ASCII table itself. So here is an overview of the message type. So REQ, request, so sent from the client to the server. This message type obviously is essential, representing the client's request for a service from the server. Another essential one is the reply, which gets sent from the server to the client. Also essential, acknowledgement sent by either the server or the client to acknowledge message receipt. So this is a reliability type of message. It enhances reliability by enabling the system to cope with message loss. If a message is acknowledged, the sender knows that their own message has reached the destination. AYA, are you alive, is sent by the client to check if the server is still functional. If a client does not receive a reply within a reasonable time frame, then it may choose to send an AYA message to determine whether the server is still operational or perhaps it has crashed. IAA, I am alive, sent from the server to the client in response to an AYA message. This confirms the server is still running. If the service fails to respond to multiple AYA messages, the client may assume it is unavailable. Another protocol message is TA, try again, sent from the server to the client when the server cannot accept new requests, typically used when the server is overloaded, such as when the buffer space is fully utilized. This informs the client to retry the request later rather than expecting an immediate response. AU, address unknown, sent from the server to the client to indicate an addressing problem. This message signifies that no process is running at the specified address and retrying will not resolve the issue. So integrity and functionality. So the essential messages are REQ and REP. These are the core of middleware communication, enabling basic services between client and servers. So additional functionality, I would say the rest of the messages. So ACQ, as we said, adds robustness to communication, ensuring messages are not lost without notice. AYA and IAA help the client verify the server's status, providing a mechanism to detect server crashes or delays. TA manages server overloads by temporarily refusing requests and signaling to try later. AU prevents futile retries by indicating that no server is available at the specified address. So these message types facilitate a well-rounded communication model for RPC type middleware. So they cover everything from basic requests and responses to handling failures, and this ensures continuity and managing overloads. Okay, and here are some examples of how we can build protocols using these different types of messages. So the different protocols are suitable for different types of networks. So firstly, we start with a simple protocol with no acknowledgement. It's suitable for highly reliable networks with minimal risk of packet loss, such as LANs, local area networks, within a single data center or controlled environment. So for example, it might be used in high-speed intranet applications where communication reliability is pretty much guaranteed by the network infrastructure itself. So such as internal corporate applications or on-premise database interactions. So the simplicity of this protocol reduces latency and resource usage, which is ideal in low failure environments. Okay, and so you can build that very simply with a request reply message combination. Now, the second type of protocol, we simply add an acknowledgement. So this is suitable for moderately reliable networks where packet loss is a possibility but not frequent, such as corporate wide area networks or regional cloud data centers. So examples, use cases, this protocol works well with for financial transactions, remote file transfers where data accuracy is important and confirmation is needed to prevent loss or duplication of messages. It adds reliability by ensuring each message is acknowledged, making it ideal for networks with occasional disruption. Next type of protocol we can build is where the response also acts as acknowledgement. So suitable again for networks with moderate reliability and relatively low latency. So this is like university campus networks, national intranets, where there might be occasional packet loss, but overall the network remains stable. So it can be used in e-commerce applications, client-server, database transactions. Now we can add even more reliability, developing protocols that include more protocol messages. So if we add the AYA and IAA messages, then we have a protocol that's ideal essentially for unreliable or high latency networks. So, so these are mainly internet-based applications, mobile networks, or international cloud infrastructure where servers might be geographically distributed far away from each other, and network disruptions and errors are more common. So it's suitable for mission critical applications where server reliability is uncertain, like telecommunication, distributed IoT systems, or international distributed databases. The AYA/IAA messages add fault tolerance, allowing clients to check server availability and manage cases where the server is temporarily unresponsive. And this protocol is often seen in edge computing setups or content delivery networks, whereas the server status checks are crucial for maintaining continuity. Okay, so this just gives us a flavor of the different kinds of protocols we can build with the most common and used message types within middleware. In remote procedure call execution, the goal is to encapsulate client-server interactions in such a way that they appear seamless to the user. Whether it's a programmer or anyone else using the middleware, ideally these interactions should function as simple operations, where the client invokes a service call and receives a result without being aware of the underlying network. From the client's perspective, using middleware should be straightforward. They initiate a service, receive a result, and have no need to consider network complexities. Similarly, on the server side, the process involves accepting requests and executing procedure calls, all while maintaining simplicity in interactions. To achieve this level of simplicity, we utilize a tool known as a stub compiler. So this tool effectively hides the complexities of message passing across the internet, allowing application programmers to focus solely on their tasks without needing to worry about network layer. In essence, it's similar to how operations function on local machines, where details of communication are abstracted away, enabling a smooth and user-friendly experience. So in a typical local setup, when we have multiple classes where one class calls another, we use what we call a compiler to handle these interactions. For example, imagine you have two classes, one we call S and one we call U. So the one named S provides a service, while the other one called U acts as a user of that service. Both classes use something called a compiler, converting them to object code. In Java, for example, the result is a .class file for each of the files. So a .class file for the S service and a .class file for the U service. And these are stored in the file system. So after compilation, the runtime environments uses a tool called a linker or a loader to link these classes and place them in memory. This tool ensures that all necessary classes are linked within the program, allowing them to operate together in memory when the program is running. So on a single machine, this process is straightforward. So compile, link, and load everything into memory, and it's ready to execute as a single unit. But things get more complicated when classes are on different machines across a network. So in that case, our two classes exist in separate address spaces, and direct linking is just not possible. To bridge this gap between the user object on one machine and the service object on the other, we need an RPC mechanism. So this mechanism relies on the middleware to facilitate and enable communication between the two. So this is where stubs come into play. We create a client stub and a server stub. The user object is linked to the client stub, while the server object connects to the server stub. The client stub is responsible for using the communication protocol to send requests, receive acknowledgements, and handle responses. And in the same way, the server stub receives incoming requests, invokes any appropriate services, and sends back results to the client as a message. So these stubs basically function like interfaces or intermediaries or proxies. They create the illusion that both client and server are on the same machine, even though they're not. They're actually on separate networks, on separate machines connected by a network. They manage complex tasks in the background, such as network communication, protocol handling, result transmission, enabling a seamless interaction. So in the past, these processes required manual handling. Today, stubs automate these tasks, so everything is done automatically in the background. The stub is generated using the IDL of the service, so the interface definition language of the service. For example, in Java, we use a simple Java interface to define the service, which is then it's run through the stub compiler to produce both the client stub and the server stubs. So similarly, if we have different languages communicating with each other and we're using something like SOAP Web Services, then what we use is the WSDL file. So the WSDL file is used to generate the stubs. The stubs basically ensure that even across machines, the service remains accessible and easy to interact with in the same way as it is in a single unified system. So here is a more visual representation of this process. We give a brief overview. So the service interface represents the interface definition of S, outlining the methods available for remote invocation. This then goes through the stub compiler, which uses the service interface to generate two stubs. We have a client stub for the client side and a server stub for the server side. And then we do our linking. So the user object is linked to the client stub, allowing it to send requests to the server, and the server stub is linked to the service. The server object is linked to the server stub, enabling it to receive requests and respond accordingly. So this setup abstracts network communication details, making remote calls appear like local calls by generating the required stubs based on a defined interface. So now that we've seen how stubs are generated and used, here's an overview of the full RPC process within the middleware. So the client calls the client stub. The client stub builds a call message, marshalling parameters, and the stub calls the specific operating system routine to send a message over a network. So the operating system then sends the message to the server network, to the server node over the network. The server node then receives a message and hands it to the server stub. The server stub unmarshals the parameters and calls the actual routine required to run the service. Call is executed and results returned to the server stub. The server again marshals the parameters, builds the result message and hands it to the operating system for transmission. And then the operating system sends a reply message to the client node over the network. The client stub receives the message and the stub unmarshals the result and returns the call to the client. So as a programmer, whether we're focused on distributed systems or other areas, it's important to understand parameter passing concepts. Different programming languages follow different parameter passing mechanisms. And the main ones are call by value, call by reference, and call by value result. For example, Java uses pass by value, while C allows both call by value and call by reference. Each language's approach to parameter passing influences how variables are handled during function calls. In call by value, parameters are copied onto the stack. The stack is a memory section for managing program data. So any changes made to a local variable in the call procedure do not affect the original variable. By contrast, in call by reference, the memory address or reference of the variable is passed instead. This allows the called procedure to directly modify the variable with changes reflected in the calling program immediately. The call by value result mechanism, also known as copy restore. So this involves copying the value onto the stack, executing the call, and then copying any changes back, overwriting the original variable. So although call by value result is used in older programming languages, it is very important for distributed programming, where it underpins the process of serialization. So serialization means making a copy of a variable, transmitting it over the network, and applying changes upon receipt before sending the modified variable back to the original machine. The key difference between call by reference and call by value result lies in timing. So call by reference implies changes immediately to the original memory location, while call by value result waits until the procedure is completed before synchronizing the changes. Okay, so here's an example to illustrate the pass by value mechanism used in the Java language. So consider a simple routine. So we have an integer I, and it's been initialized to a value of 2, and we have a method and we're calling it do something. So we can pass values to the do something method, and do something then does something. When I is passed to do something, it is first printed, and initially it should print the number 2 because the value of I is 2. If, however, then we assign a new integer value, so in line 8 you see that it says I is equal to new integer 2000, then I will acquire a new address. So it'll point to another address in memory, completely separate from the original object when we said I is equal to new integer 2. So inside do something, printing I now will show 2000. However, if we return, so when control of the program returns to the main method, printing I on line 4 should still show number 2, because Java is passed by value, meaning the original I remains unchanged. In a distributed systems context, so there are applications for RPC, parameter passing. Addresses on one machine are meaningless to another machine. Each machine's address space is unique. Consequently, if one machine sends an address to another, it'll mean nothing to the other machine. It will definitely, almost certainly not correspond to the intended data. So to address this, RPC can substitute call by value result or copy restore in place of call by reference. This approach involves serializing the data, sending it over the network, allowing changes on the receiving machine, and then copying the results back. Another method that we can use involves using machine-independent references. Here, both the variable address and the sender's IP address are included. So this ensures that any modifications reflect back to the originating machine. Middleware typically supports both approaches, but programmers have to choose wisely based on performance considerations. For example, excessive use of machine-independent references will slow down the program because each reference involves additional network calls. So a clever programmer should instead choose to batch and serialize data, sending it all at once, applying any necessary changes, and then send and update data back in a single transfer. And deciding between these two approaches needs balancing data flow and network latency to optimize program efficiency. So which method to use should be designed carefully when designing the computer program. So finally, this ties back to the concept of marshalling and unmarshalling, which handle data preparation for network transmission, which we'll talk about next. So let's talk about parameter handling in RPC. And this specifically is a process of packing, also known as marshalling, and unpacking, also known as unmarshalling. So the key concept are marshalling and unmarshalling. When data is sent from a client to a server in an RPC, it needs to be packed or packaged into a message. This process is called marshalling. Upon reaching the server, the data is unmarshaled, unpacking it back into usable parameters for the server's procedures. Okay, so different machines use different methods of storing bytes, which affects how data is marshaled, and there are two different methods, also known as two types of endianness, which can be used on different machines. So if a machine uses the big endian method, then it stores the most significant byte at the lowest memory address, essentially putting the big end first. The little endian method stores the least significant byte at the lowest memory address, placing the little end first. So these terms were inspired by Jonathan Swift's Gulliver Travels. So these are novels that were written a long time ago. So in these novels, societies were divided over whether to break an egg at the big or little end. So these are one of the societies that Gulliver meets during his travels. So they use the developers of how data is passed into computers decided to use the same terminology, big endian and little endian, as were used within the novels. So similarly in computer systems, these systems often disagree over byte ordering, needing RPC mechanisms to handle these differences carefully to ensure data compatibility across these differing systems. So this distinction in endianness is very important for RPC. It ensures that data transmitted between machines with different byte ordering conventions can be correctly interpreted regardless of the sender or the receiver's architecture. So here's a simple example. So within an Intel machine, which uses the little endian method, an integer value of 5 in this example is stored with the least significant byte first. So the value 5 is represented as 00000005 in memory, starting from the lowest address. However, on a Spark machine, and Spark machines use the big endian system, here the most significant byte is stored first. So the same value 5 would appear in memory as 05000000 with the big end coming first. So this represents a communication challenge. So when data is transmitted from an Intel machine to a Spark machine, the different byte orders mean that the Spark system can interpret the number 5. Instead of seeing it as a 5, it might interpret it as 83,886 and 80 83 million, sorry, 886,080, a completely different value than 5, obviously. So the solution is that the middleware needs to recognize this difference and deal with it. Okay, so the receiver, in this case the Spark machine, must know how to unmarshal the data correctly, adjusting for the byte order difference. And middleware often defines a standard data representation for all data types to accommodate both endianness formats. The sender specifies its byte order, and the receiver performs any necessary conversion to interpret the data correctly. When designing client-server interactions or interactions for any distributed system over a network, one important consideration is how to locate the server. So in the past, this was achieved through a method called static binding. In this approach, the client program was written to connect to a specific server by hard coding the IP address directly into the code. So while this method is very simple and works a lot of the time, it lacks flexibility. The main problem of static binding is that it doesn't handle changes well. If the server's IP address changes, or if the server goes down and its data is moved to another machine, then the connection will be lost, and that requires manual reconfiguration to re-establish communication. To address this limitation, more adaptable solutions like naming servers have been developed. These provide a way to dynamically locate servers, enabling greater resilience and flexibility within distributed systems. Okay, so dynamic binding. So this slide explains the process within RPC, within middleware, illustrating how a client dynamically locates and connects to a server. So here's the process of dynamic binding. The first step is called endpoint registration. The server on the server machine registers its endpoint with the DCE daemon or daemon. This is the distributed computing environment daemon that holds the port numbers for all the applications within a machine. So you're all familiar with what a port is. It's basically the address of a particular application within a machine, how to connect to it and how to access it. So the endpoint table is updated within the daemon, and then this endpoint acts as a unique identifier for the server's available service. Then the next step is what we call service registration. The server then registers its service with a directory server on a separate directory machine. This step makes the service discoverable for clients. Then the next step is server lookup. When a client on the client machine wants to access a service, it first contacts the directory server to look up the location of the server offering the desired service. Once this has been looked up, we then request the endpoint. So after identifying the server machine, the client asks the DCE daemon on the server machine for the specific endpoint associated with the service it needs. And then we can execute the RPC. With the endpoint information in hand, the client can now directly connect to the server and perform the RPC. So in summary, dynamic binding allows clients to discover server locations at runtime rather than hard coding them. It provides flexibility in distributed environments by using a directory service and endpoint registration. So RPC enables, using this method enables scalable location-independent connections between clients and servers. And here's the text of what I just described. So in distributed systems, a specification language is very important for defining the service interface. This enables the creation of stubs, which we talked about earlier, and enables describing available operations to the calling machine. This language specifies the service routines or the procedures or the methods that the client can invoke. For example, in C++, we will typically use class definitions, while in Java, we use interfaces to specify these services. Each language has its own conventions, and for web services over the internet, it's very important to check how each language describes the service to external systems, often through interfaces. Although some languages might rely solely on class definitions if interfaces are unavailable. So specialized interface definition languages, or IDLs, exist to facilitate mixed language programming. For example, WSDL or WSDL, the Web Services Description Language, which uses XML as a universal format to translate service descriptions across different languages. So that would be used if we want different languages to talk to each other. So the WSDL, as you've seen previously in the Web Services talk, the WSDL will be used to describe the services that are being exposed and that are accessible by different clients. So using an IDL, an interface definition language, allows the stub compiler to support interoperability, so the client and server can be written in different languages. This capability is a fundamental objective for middleware to enable seamless communication between applications written in diverse programming languages. One of the fundamental principles of building distributed applications is handling failures effectively. While failures can occur on a single machine, they are more common in distributed environments, especially across networks. For example, network connectivity might fail, or in a cloud setting with thousands of interconnected machines, components can frequently break down so that they can be and being replaced. So these frequent failures require that middleware can detect and manage them. Failures can be due to various reasons, such as communication breakdowns or node crashes. A node or a computer might crash temporarily and recover, or it could fail permanently. So a system must be equipped to handle these possibilities. So generally, there are two types of termination. So the first type is normal termination. So normal termination is the ideal scenario where no failures happen. The client sends a request, the client receives a reply, and the interaction concludes smoothly. So that's normal termination. The other type of termination is abnormal or exceptional termination. So in this case, the client sends a request but does not receive a response due to a failure. To handle these situations, middleware can be designed in three main ways to address different types of failures, ensuring the distributed system remains robust and reliable. So within middleware, handling failures is an important aspect, and there are several ways to approach this, each with different reliability levels. So first we'll have a look at exactly once semantics, then we'll look at most once, and then we'll look at least once. We'll look at how they handle normal termination and how they handle abnormal termination. So a normal termination, you send a message and you receive an acknowledgement or a reply, and you know for sure that your message has been received at the other end. In abnormal termination, you don't receive a reply or acknowledgement due to some network connectivity problem. So in such a case, you don't know whether your sent message has been received at the other end. So if that happens, how does the middleware handle the situation is quite important. So let's start with exactly once middleware. So this is the most secure and reliable, but also the most challenging to implement. In this approach, the middleware ensures that the call is executed exactly once, even if there are network failures. If a reply is received, it guarantees that the operation was completed precisely one time. If no reply is received, it confirms that the operation did not occur. To achieve this, the middleware needs transaction capabilities, which involve tracking and validating each step of the process. This level of reliability is essential for critical applications like banking transactions. For example, when transferring funds, exactly once semantics ensure that £100 is transferred only once, avoiding accidental multiple transfers. The next type of reliability is at most once semantics or middleware. So this is the simplest approach. Here the middleware attempts to send a message only once. If it succeeds and receives a reply, then the call was executed once and only once. However, if there is no reply, the client has no way of knowing what happened. The request may not have been executed, it might have been partially executed, or could have been fully executed, but failed to return a response. This approach is suitable for low-risk scenarios like local networks or non-critical tasks. Example, sending a print job. However, it lacks robustness for complex applications where reliable execution is very important. Finally, we have at least once middleware. This approach ensures the message reaches its destination by repeatedly sending the request until a reply is received. However, if a reply is eventually received, it's uncertain whether the call is executed once or if it has been executed multiple times. The receiving machine may have executed the request several times, especially if it processes each repeated request. This approach is useful when it's acceptable for an operation to occur multiple times, like deleting an item from a database, where multiple deletions have the same effect as one. However, it can be problematic in cases where repeated executions cause problems. So in summary, exactly once is highly desirable for critical applications requiring absolute reliability, but is complex to implement, requiring transaction handling within the middleware. At least once is easier to implement and suitable for scenarios where multiple executions are harmless, but is unsuitable for tasks that cannot tolerate duplication. At most once offers a simple, minimal approach, but it's generally insufficient for applications requiring reliability and consistency. So understanding these semantics and knowing when to apply each type is very important for designing middleware suited to different applications. So thank you very much for viewing this talk and listening to it. And here's a review of what we went over. So first we talked about protocol issues, fragmentation and reassembly, the message types that can be sent and received, and the different protocols that can be built using those message types. We looked at binding and integration, locating services, client and server stubs, how stubs are created and their role in enabling communication over the network. Parameter passing semantics, we looked at marshalling or marshalling wire representation, and we looked at server specification languages, IDLs, and their role. And finally, we just talked about the treatment of failures within middleware. We looked at different semantics which in turn impact on underlying protocols.